Okay, so in the flow experiment, we actually did what I was saying here. It's a 3-parameter model, and we used the y equals at squared plus bt plus c model, although we could have used the vertex form. But that requires us to estimate where the vertex is. And as it turns out, our data is a little weird with the vertex. And the reason for that is when you get close to the vertex, which is what occurs when the flow stops, there's a little surface tension in the water. Okay? And that prevents it from acting exactly according to the rest of the model. It changes the model a little bit when you get down toward the end. Okay? So we probably don't want to use this model, but what we did, I'll just say probably avoid, avoid this model, because this model would require you to know where the vertex is. Okay? And if you assume it's where you think it is, you're probably off. So we use this model, we graph, and we've got like 5 data points or something like that, so we sketch a curve, and we pick 3 points. Don't get too close to the vertex. I didn't really warn you about that because the main thing is knowing how to do this. But I'll comment on it now. And if I do give you a problem like that and you decide to pick a point too close to the vertex, I'm not going to penalize it. Okay, I'm just kind of giving you an indication though of the nature of the modeling process. Okay, so 3 points. Give you 3 equations. Which give you the values of the parameters A, B, and C. Okay? Then we compare the predictions. With the data points. And that's relatively easy to do. Take the t-coordinate of this point, plug it into the model, and see what it predicts for your y value. If the curve is really like this, it's, you know, the observed value is a little higher than the actual y value, right? And you note that. And you kind of do a little statistics with that, very little because we're not doing statistics in this course, but I could ask you to make some comparisons, okay? Now the other thing about this model, the point I really want to make now, is that, as you should by now understand, but maybe don't, if you take any 2 points on a quadratic model, and calculate the slope, okay, you get the same thing you would for any other fundamental triangle, it has the same midpoint. Now that's a unique property of quadratic functions. Well, that leads to the fact that the graph of the slope versus midpoint is linear. Okay? So this means that if I was to graph slope versus midpoint, the slopes are all negative, so I'm not going to leave myself a lot of positive y values, but the slope versus midpoint is going to look like this. Okay? So really all you need to do is calculate two slopes and midpoints, gives you 2 points, and you got your linear function, because you only need 2 points, right? I would calculate it for 3 just to check, make sure those 3 lie on a straight line. If they don't, it means you miscalculated something, so you go back and fix it, because they will lie on a straight line if you've done it correctly. Okay? And let me again urge you, when you're doing work, you check yourself. You don't learn as much if you don't check yourself, because you never know if you're wrong. Okay? Till I tell you. And you learn much less if you have to wait for me to go over your homework and get it back to you next time and tell you. You learn it right away if you do your check, right? Reinforces a process, corrects it right there at the time when it needs to be reinforced and or corrected. Okay, well, okay, anyhow, you get the slope versus midpoint. Now, what's the slope mean? Means the average rate of change of y with respect to x, or in this case, actually I should use t. I should have used t here. Okay? I mean, there are a lot of quadratic models that use x. So it could be either, but since we're talking about the flow experiment, I should have used t when I started. Okay, so the slope means the average rate of change of y with respect to t. What's that mean? What's y? You got your data. You got depths and you got times, right? Which one of those is y? Probably the one that isn't t. Now, of course, if you understand these models, and you need to understand this very well so you don't have to keep being reminded of it, okay? Because if you understand it that well, you'll be able to interpret other models, okay? You'll be more likely to be able to interpret other models. Now, there's some really tricky interpretations out there, and I'm not going to lay those on you, okay? But if it's depth versus time, pendulum period versus time, pendulum frequency versus time, angular velocity of that strap that we measured versus time, temperature versus time, those are all things that are easy to understand, okay? There are plenty of things that are tricky to understand. Penalty things that I have to look at a couple of times. Wait a minute, what's that mean? Okay? Even though I know the process to figure it out conceptually, it might take me a few minutes. Okay? And of course there are fields that I don't know enough about to understand what the interpretation means. So then I have to learn a whole new field, master it, and win a Nobel Prize in that field so I can interpret the graph, right? And sometimes it's a field without a Nobel Prize, so why should I bother? Well, yeah, obviously, tall tale, but yeah, I've only won Nobel Prize in a couple fields, you know, I'm kind of a wimp. Right, okay. Back to reality here. Average rate of change of what with respect to what? Y means? Pardon? I'm sorry. Lake was intentionally coughing to obscure your incorrect answer. But what was it?
Well, my incorrect answer was Y.
Oh yeah, it's Y. So, but it is the average change of Y. So, what's Y mean? Again?
The depth.
Yeah, you knew. Okay, good thing Lane coughed. Okay, Lake.
Thanks, bro.
Did I call you Lane before? Yeah, I had a student named Lake that sat right there last year. Good guy, good student. So there's a history. You got to maintain that history, right? Okay. So anyhow, average rate of change of what? Of depth with respect to time. Okay? And why is it that? Right? The rise is equal to the change in Y. Run equal to change in T. So typically, the way we measured it, Y was in centimeters, T was in seconds, right? Anyhow, the slope is the average rate, which is delta Y over delta T. What's delta Y measured in? Same thing Y is measured in. Delta Y is the change in your Y value, right? So, you know, water's going down here, your Y value changes. Okay? So maybe the Y value is here when T equals 10 seconds, and it's here when T equals 20 seconds, right? Okay? So your change in T is what? Let's say you go from 10 seconds to 30 seconds. What's the change in T?
20 seconds.
20 seconds. That would be the run of your fundamental triangle on the interval from 10 seconds to 30 seconds. Okay? Now what's happening to the depth during that time? And it's doing this. What's this indicate?
Decreasing.
Huh?
Decreasing.
Yeah. Depth is going down, it's decreasing, right? And you know that's what happens when things leak out of containers. Assuming gravity's in that direction. Okay. So what would delta Y be? Show me. How big is delta Y? Are you watching? Want me to do it again? It's not going to be exactly the same. Okay, delta Y, one of you at least thinks it's about like this. That's in the ballpark. I said, hit 10 seconds and at 20 seconds, right? Yeah. Okay? So what would that be measured in? What did we measure Y in?
Seconds.
Sorry?
Seconds.
No, that was T. Y is your depth. We don't measure depth in
Centimeters.
seconds. Time is in seconds, right? So Y is in what units?
Centimeters.
Centimeters, right? So this is in. So the change in Y has to be in centimeters. Okay? Actually, I think when we did this, I probably gave you the depths in millimeters. No, but, you know, you change that to centimeters, and miles, or parsecs, or whatever you want, okay? But in that case, we'll talk about now, could have been centimeters over seconds, could have been millimeters per second, which would make the numbers different, but the meaning would still be the same, okay? Now, what's that tell you?
The change in depth over a certain amount of time.
Yeah. And what's that mean? Here, it does this. Everybody see that? It was incredibly graceful. Do you want to see it again? I don't want to take a chance. That was more or less perfect. It's going to be on tape. We can step over here and do it again. How's that? Is that equally graceful? Okay, yeah, probably not. Like I said, I didn't want to risk my reputation. Okay, so centimeters over seconds. Now, where did you have more centimeters per second in my demonstration?
Top.
Earlier or later?
Earlier.
Earlier. How could you tell? What was my hand doing earlier differently than it was doing later, other than being incredibly graceful both times?
Dropping faster.
It was faster. So your delta Y over delta T tells you how fast. The rate at which depth changes in time is how fast the water surface is moving. Moving faster up here than it is down here. That was kind of exponential, so don't take that literally. Okay? Make sense? So you have to understand what this means. Okay? If Y is in dollars and T is in years, then what does the rate of change mean?
Dollars.
Still means change in Y divided by change in T, but it's a different model, right? You still have your fundamental triangle, your change in Y, your change in T, right? You've got delta Y. Didn't leave myself much room, did I? Delta T. And slope, which is delta Y, rise over delta Y over delta T. Okay, so if it's dollars and years, let's say dollars and hours. What's the meaning of delta Y over delta T?
Change in dollars per hour.
Sorry?
The average change in dollars per hour.
I'm sorry, you know, pretty ignorant. Just got these things cleaned the other day. I should use them, huh? Okay, so. This thing's dinging in my ear for another 10 seconds, but say that again.
Average change of dollars per hour.
Average change rate, average change of what?
Dollars per hour. Dollar money.
Oh, money. Yeah, okay. Could be an average rate of change of wealth. Of course, it could be positive or negative depending on whether you're getting money or spending it, right? Okay. Now, you said average change, so I want to gently correct you on that. It's not average change. It's average rate of change, and you got to use the right words. Okay, people continue to misinterpret this central concept in mathematics and in Western civilization, and it really is central. Okay, we would not have technological society unless this thing had been analyzed properly. Okay? So it's real important. It's real important for understanding the world. whether it's finance, engineering, psychology, anything. Okay? You need to understand this concept of rate, which is why I'm emphasizing it today. Okay? And we've talked about it many times, and I've asked you questions about it. You know, you'll temporarily answer it right, but now's when you need to lock it in. Okay? This whole process of understanding what the rise tells you, what the run tells you, what it means to divide the rise by the run. Okay? The average, the meaning of what it means to divide a change in one quantity by a change in another. So if you change the number of dollars over the change in the time on the clock, if, for example, you're getting this by working for a certain number of dollars per hour, that's going to be the number of dollars per hour. Okay? If it's GDP, gross domestic product, okay, which is important, especially going to be investing money and understanding the economy to some extent, then it's the change in the number of dollars produced per year usually, okay? Divided by the number of years, okay? And that's often expressed as a percent, 2%, 3%. You know, above a certain amount, you're beating inflation, below a certain amount, you're not, and go from there. Okay, they're very important concepts. Okay? So, we need to understand rates.